It was best. So in this video that I want to introduce, most of people don't know about this kind of inequality called the Vander Corput inequality. And basically it has like several versions, but there are like two versions. One is related to the number theory, one is not. Okay. And this video that we will introduce the simple one. Okay, so this is basically, let me just write down the statement. So we'll take H to be here per space, or basically you can just some inner product space. Okay. Uh, and then let's say V and the U1, U2 up to UN are univector. Univectors belongs to H. Okay. Then so if you take V with UI and you compute the inner product over here per space and you do the square. Okay, so this is tricky. You sum over all the inner product and you take all the square. So you can imagine that this is V, and then this is U1, U2, and up to UN. And you compute inner product, take the absolute value, and then this will less equal to all the pair correlation. So you take all the pair correlation. So I and J less equal to N, and the UI and the UJ, and take absolute value. Okay, also a Hilbert space over H, so inner product of H. Okay, so this is the Vander Corput inequality. And this inequality looks very similar to the Cauchy-Schwarz, but actually it's not so trivial to prove. You can try to prove by yourself. Okay, so let's just write down a proof. Okay, so proof. Right, so this is, so we start from the left-hand side. Okay, so it's non-trivial. The proof is slightly non-trivial because somehow it's hard to control for its absolute value, right? So the key idea is that actually for this kind of any kind of I, right? So for all I, then this one is basically complex, right? So I can write as sorry, write as this guy for some epsilon I, which is unit sorry, which is a complex number with absolute equals to 1. Right, so basically I just take out a face. So I just take out a face called VUI. Okay. So that means that I can write absolute value as the following: VUI and the epsilon. I use this epsilon I complex. Okay, so let me just write complex conjugate here, so that I can write absolute value as this. Okay, so that means that the right hand side is basically this VUI, I from 1 to n. I can write as I from 1 to n, and the V UI and the epsilon, let's say epsilon I, right? So I just write as this. And now it's very simple, right? So now I can use, so I can write as this. Okay, so I can write as this. V and I from 1 to n, epsilon I UI. Okay, so now it's a two vector, so I can use Cauchy-Schwarz. Okay, so Cauchy-Schwarz tell me that this guy square, so now I can square it. Square it is that so equal to the inner product V and the inner product of this guy, right? So it's Okay. Right. So now this guy is 1, and then this guy I can write as summation of ij epsilon I star epsilon j and ui ujh. Okay, so now whatever it is, right? I can use a triangle inequality. So I can bound less or equal to take the absolute value. So it's let me just write it this way. So you take the absolute value and use triangle inequality. So it's basically this. Okay, because these are like unimodulars, right? So it's just 1. Okay, so let's finish the proof. This is ij ui uj. Okay, so this is a proof. Okay, and there is a very simple application. Okay, so this application is basically is one can use. So basically one can use. So idea is that one can use a test vector u, sorry v to detect the pair correlation of u, ui or uj. Okay, so for example, there's a theorem. So this theorem tells you that if v and ui for all h are greater or equal to delta for all I, let's say delta is some number that's equal to 1, then what? Then there exists uh n squared delta squared divided by 2 pairs. So pairs meaning that is ij where it belongs to like n cross n. So we can find at least n squared delta squared divided by 2 pairs such that the pair correlation is large, such that the pair correlation is delta squared divided by 2. Okay, and this is simple, so let's write down the proof. So proof. So we just use the Vander Corput inequality that we just derived. So let's tell you that. Let me just write down I from 1 to n, and u say ui, and with v, and you take absolute value squared. That's equal to pair correlation. So ui uj. Okay, and it's easy to prove this. It's easy to prove by okay. So from this, right? So this tell you that this is at least, let's say delta square n square. Okay, and the reason is that my assumption is that they are every basically delta, right? So this is delta. Okay, so yeah, delta square n square. So you get sum of them, which is greater or equal to this. And so this tell me that the contribution of those ij with this constraint, let's say ui uj, that's equal to, sorry, that's delta squared divided by 2. But you take all you ask what's the contribution of ij such that it's delta squared divided by 2. Need to is at most, right? Is at most delta square n squared divided by 2, right? Because because they need to sum at least greater or equal to delta square n squared. So you take the contribution of that ij, which is small enough, right? Basically, all its contribution is at most delta square n squared divided by 2. Okay, so that means let's prove the results. So basically, this tell you that if basically the left hand side is large, the right hand side must be large enough. So you can always so this tell you that if there's enough large enough, then must exist large enough pairs, such that for this pair correlation, there must you must find some large correlation. Okay, so this is the idea that one can use this kind of test to test whether all of this vector has a pair correlation. Okay, so see you guys next videos.